All right, welcome everybody to this session on showcasing and exploring papers that have been published in AI. Today we're going to be talking about object detection and fusing data. We have two speakers today. So I think Natasha is going to talk to us about you only look once, a very efficient method for object detection. So if Natasha's there, she can share her screen.
Yep. Hi, everyone. Let me share my screen quickly. Okay. Can everyone see my slides?
Yep.
Yeah.
Awesome.
Great. Cool. Am I good to go?
Yep.
Yeah.
Awesome. Thanks.
Great. No worries. Great. So far in the Summer of AI program, you all have been looking at these cool things, ChatGPT, stable diffusion, transformers, and whatnot. And while all those are very advanced topics that are very exciting, there are some things that are very basic when it comes to neural networks as well, and image analysis, right? So object detection is one such topic. And what I'm going to talk about today is this particular network, or the series of networks called the YOLO family of convolutional neural networks. And YOLO stands for you only look once, and I'll explain why this particular network is named that way. So just to give a little bit of background, object detection networks evolved in sort of two different eras. Before 2013, they were making slow progress, but after 2013, after the introduction of AlexNet, it escalated in their improvements, these object detection models, but they also split into two different types. So people were working on one-stage object detectors as well as two-stage detectors, and they took on their different parts. And YOLO is one such one-stage object detector. So the difference between, so the first era was called the traditional era, and the second era was called a modern era of object detectors. And then the difference between these two types of detectors is that, as their names suggest, two-stage detectors literally have two stages for these detections. So first, what they do is that they have a generation of region proposals. So they will look at the images and decide, where do you think these objects are probably situated or located? And then they would send those proposals through a CNN and perform classification and regression. In contrast, one-stage detectors, they would look at the input image at once, perform all these feature extractions at once, and then output their class probabilities and the object locations as well. So that's why they're called one-stage detectors. So SSD and YOLO are one-stage detectors, and popular two-stage detectors are RCNN, fast RCNN, mask RCNN, and so on. So when it comes to YOLO architecture itself, I should be updating this list actually. I think YOLO is at its version 7 now. I think version 7 came out in July this year, as I remember. So it has been evolving consistently, and this particular diagram is actually from YOLO v1, and it involves a very simple single deep convolutional neural network, and it would have all these convolutional layers, and at the end they would have like a fully connected layer where you sort of calculate all of the positions and the class probabilities of objects of your input image and perform regression at the end to predict what your objects are, right? So because they sees the entire image during your training and testing time and implicitly encodes all of this contextual information about the classes, this particular architecture is named YOLO. You only look once, right? There's no region proposal involved in this particular architecture. So how does YOLO actually work? So when it comes to image classification, let's say I give you this image and I ask you whether this is a cat or a person, right? Even though this cat is wearing a hat, that's a cat, right? So I would say, oh, that's just a cat. That's how image classification works, right? We are not worried about where the cat is actually located in the image. But when it comes to object localization, I want to know exactly where the cat is located in this particular picture, right? So in addition to the fact that the class of this particular object is a cat, I want to know where the bounding box that encloses this cat is in the image as well, right? So that's object localization. So for object detection problem, how the training works is what we would feed the neural network, or the ground truth would include this image, and then the classes of the objects in that particular data set. Let's say I'm trying to detect cats and people. So my data set would have both cat images and images with people, right? And then I would want to feed it with bounding boxes of where each of those objects are as well, right? So that's ground truth for object detection or object localization. And then how YOLO works is, so now what I'm talking about is how YOLO is working. For a single object, how we encode this information for YOLO is with this array of numbers, right? So we have 7 numbers. So the first one is a probability of an object being present in the particular image. We call this an objectness score. And then the next 4 numbers are related to the bounding box. We provide it with the center coordinates as well as the size of the bounding box. And then the last 2, because we're trying to detect 2 different things or 2 different types of objects in this particular data set, I'm trying to detect cats and people, right? So I'm going to give it class 1 probability and class 2 probability, right? So I've just plugged in some dummy numbers here. So class 1, I'm going to consider cat. Class 2 would be people, right? So because this is a cat, I've encoded that as 1. Okay, so that's for a single object in an image. But what if there are multiple objects in an image? So this particular image has a cat and a person, right? So how do we work with this? In that case, YOLO would divide an input image into some number of grid cells, right? So we'll call this S by S grid cells. And each cell would have this vector or the array of values now, right? So a grid cell will be responsible for detecting an object if that center of the object falls into that grid cell. Otherwise, it's not going to worry, that other grid cells are not going to worry about the object, right? So for an example, if we consider this particular grid cell from the top corner of the image, that's empty, right? There's nothing in it. So that's not going to encode any of the numbers for its array. This particular cell has the center of the cat in it, so it will have some numbers with respect to the corners of that particular grid cell. And this has the center of that person. So these are dummy centers that I just put just to explain this. And that cell would also have some numbers, right? So if you look at the class probabilities for the cat center, the grid cell that has the cat center will have the class as 1 for cat, but the next cell with the person center would have class 2 as 1, right? Because that's a person. So this happens during training, and YOLO actually learns how to encode these numbers, right? So at the end, because this input image is divided into S by S grid cells, the size of the output tensor becomes 3D, because each of these cells has this array of numbers associated with it, right? And the size of the output tensor becomes S into S into 5 plus C, right? So 5 is probability, the objectness score, and the 4 numbers for the bounding box. And then the however many number of classes that you want to look at in this particular data set, right? So that's all good. These 2 centers are in different grid cells. So the grid cell can easily handle this case of having multiple objects in an image. But what if there are multiple objects in one grid cell? What if the centers of multiple objects fall in one grid cell, right? So a case like this. If this is the case, YOLO uses something called anchor boxes. So the concept here is each grid cell of this image will have a number of predetermined boxes or priors that are assigned to these grid cells, right? We call these anchor boxes. And given that we are just trying to detect two different stuff in this data set, let's say we have assigned 2 anchor boxes per grid cell, right? So we pick these according to sort of like the common aspect ratios of objects in our data set, previously training this YOLO network, right? So anchor boxes are chosen by applying k-means clustering to the ground truth bounding boxes of the data set and choosing a desired number of most common box sizes, right? So if you apply k-means clustering to the ground truth bounding boxes of this particular data set, people are going to be similar in their aspect ratios. Cats are going to be similar in their aspect ratios, right? So we can easily pick out some common anchor box size for almost all people in general, and some common anchor box size for cats in general, right? So then we assign these 2 sizes of boxes for all the grid cells. And then what we do is, because these grid cells have 2 anchor boxes now, they can associate 2 sets of predictions, right? So the first one can be used to predict a person, the red anchor box, and the green anchor box can be used to predict a cat, right? So the first set of numbers, the first 7 numbers can be used to predict a person if there's one, and the second set can be used for a cat, right? And then the size of the output tensor now increases by the number of anchor boxes that we use per grid cell as well, right? Because we have 2 sets of predictions now per grid cell. So the size becomes S by S into B plus 5 by C, right? So the inference of a bounding box during training happens as an offset to these anchor boxes. Normally, YOLO doesn't predict the absolute coordinates of the bounding box's center. Instead, it predicts offsets, right? So it's very relative to the top left corner of the grid cell and the anchor box itself. And then, so this is the most commonly used architecture, which is the YOLO v3 architecture. In contrast to the YOLO v1 architecture that I showed you guys earlier, this has 3 detection scales, which helps to detect different sized objects in images, small, medium, and large objects as well. And then each of the detection heads will have 3 anchor boxes per detection head. So altogether, there are 9 anchor boxes associated with YOLO v3. And then, because of this, in YOLO v3, you have a large number of predictions that's possible to be done, right? Because at each scale, the grid cell size is also different. The loss function of YOLO v3 is composed of 3 different parts. So we have a localization loss, which sort of works on the bounding box attributes and work whether the bounding boxes are predicted correctly and penalizes that. Then we have an object confidence loss, which penalizes the objectness score. If you remember the first number of that particular vector, they penalize it for bounding boxes with objects as well as for bounding boxes with no objects, because we want the network to learn to detect objects, not the background, right? And then we have a classification loss part as well, which sort of penalizes the class probability of the object. The accuracy metric used in YOLO is mean average precision. It will calculate the IOU between your predicted bounding box and the ground truth bounding box, then calculate the precision and recall, the precision recall curve, the average precision, which is called AP, and then you calculate the mean average precision across all of the classes. The higher the score, the higher the mean average precision, the more accurate your model is, right? I put all of the formulas in here if you guys want to look at later, but most of you might already be very familiar with what mean average precision already is. And then that's all good, but YOLO is very susceptible to multiple detections from an object, right? If we don't do anything about it, this is what your detection is going to end up looking like, right? You will have multiple detections because each grid cell is trying to detect something, right? So this is where non-maximum suppression comes into play. And we sort of clean up multiple detections of the same object based on the class probability scores, right? So for the predictions of each detection object, we keep the bounding boxes with the highest class confidence scores, which are above some threshold that we set before training. And then we discard all of the bounding boxes that will have a lower objectness score and pick the bounding boxes with the largest objectness score, and then compare the IOU with all of the remaining bounding boxes, and also discard everything that has a higher IOU, common IOU, right? So after applying non-maximum suppression, we are left with just the correct or just one detection per object, right? So the advantages of YOLO is mainly the speed of it. Actually, it's incredibly fast. And because of this, it's very well suited for real-time object detection. This diagram is from a paper I found. I forgot to add the source here, actually. But it compares the frames per second speed among these two-stage object detectors and one-stage detectors. I think low and high means low resolution images and high resolution images. And you can see that YOLO with high resolution images, it's like 10 times faster than, sorry, not larger than 10 times actually, faster than fast RCNN in low resolution images, right? It's 91 and fast RCNN is just 5. So because this is very fast, it's very suitable for real-time object detection problems, right? And then the authors also mentioned that YOLO is very much capable of learning generalizable representation objects, because even though, and how they prove that is by training YOLO on natural images, but then applying the trained network on artwork. And why YOLO is performing well in that case is because even though there are pixel-wise differences in these two types of data sets, they're just looking at the location and the shape of objects, right? They're not analyzing the image pixel-wise. So it's very capable of learning generalizable representations as well. A few disadvantages or limitations of YOLO might be that accuracy-wise, it might not achieve as accurate results as two-stage detectors sometimes, but I think this has been surpassed now with a lot of modifications that has happened. And then because each grid cell will have a predetermined number of anchor boxes, there's a limitation to how many predictions each grid cell can make. Even though we can shift this number of anchor boxes around, it's sort of limited a little bit. And because of this, it might struggle to detect small objects that are, or images that have a very cluttered set of objects, and so on. But I've seen that there's a lot of research work that's happening on these areas as well to improve these. So some of the recent or more popular applications of YOLO has been in autonomous driving, pedestrian detection, and things like pothole detection, traffic cone detection and stuff to help with autonomous driving. And then it has been used in aerial perspectives, and drone driving as well to identify various geographical locations and various other landmarks from the perspective of UAV vehicles. And then it has been used in agriculture a lot for fruit counting, to find out damaged fruits, to find out whether the crops are ready to be harvested or not, and things like that. So this tomato one, they were looking at whether tomatoes are ripe or not. So things like that. And then YOLO has been widely used in medical image analysis as well. Things like 2D kidney recognition, detecting these fundus lesions in the retina, bones detection, stroke lesion detection in MRI images, and so on. And then myself, I've used an improved version of YOLO for this problem of pigmented iris freckle detection, where these iris freckles were working as a biomarker for skin cancer detection. And with our improvements, we were able to sort of detect these tiny freckles in the eyes or the iris without the use of anchor boxes, actually. So it has been very useful in a lot of medical image domains as well. So in summary, YOLO takes in the image, the classes of the objects in these images, and bounding boxes of the objects as they are trained in ground truth. It would divide the image into grids, assign predefined anchor boxes to each cell, and use those anchor boxes to predict the bounding boxes during training with respect to the anchor boxes. The later versions of YOLO has multiple detection scales. It would calculate a 3-part loss and apply non-max suppression if there are multiple detections of the same objects. So that's pretty much how YOLO works. Thank you. If there are any questions, I'll be happy to answer.
All right, thanks, Natasha. That was great. Any questions for Natasha? Maybe I can ask a few. There are some other bounding box related object detection things like transformers, mask RCNN. How does YOLO compare to them? Is it like faster, or is it like
so with mask RCNN, I think the advantage of mask RCNN is that it can perform segmentation as well. So YOLO just provides the classification and literally just the bounding box as the output, but mask RCNN will give you the segmented borders as well. Transformers, I believe it's faster, but I'm not too sure about what the output of the transformer is. It's probably better than YOLO though.
Right, yep. I think it's called DETR, I guess DETR. Yeah, my feeling was that the YOLO was probably the fastest of them all, but
right. I haven't seen any comparisons between YOLO and transformers, to be honest. They always just compare between just the RCNN family and SSD and then YOLO. It would be interesting to see which one's faster in that context.
Yeah, there's a good question in chat.
Oh, sorry, I didn't see it. Is there any applications of YOLO on 3D images? I haven't personally seen any, I think, but that's no reason that you shouldn't be able to use it. Maybe not directly, because you might have to change the way the encoding works in YOLO to give you like the correct output tensors for each of the, so you'll have like a 3D grid cell then for each of the 3D images. But yeah, I haven't seen any though. Which might be a useful way. Yeah.
Yeah.
Can we tweak YOLO to perceive distance between two objects? What do you mean, as in distance, as in just 2D distance? If it's just a 2D distance, you can't just calculate it with the predictions that YOLO provides.
Hi, Natasha. Let me just clarify the question. So, I mean, let's say if you're using YOLO on some CCTV camera to detect like a social distance between two
Yep.
person?
Oh, okay.
Like,
In that case, they've actually done. I just saw some research where they actually calculated social distancing between people during COVID times using YOLO. And YOLO, I don't know if they still use it, but YOLO was used at some point in Tesla for autonomous driving. So they do have like a depth perception. Definitely, it can be used.
I see. Thank you.
Yeah. Are there considerations around varying the size of bounding boxes? Smaller boxes for dense objects? Can these? Yes. So you have, this code is open source. You have your you can change your anchor boxes to be whatever sizes you want. If you heard what I said with my particular research, working with these iris images, I actually discarded all of the anchor boxes and worked without anchor boxes at all. Or you can set like a fixed anchor box size for all of the objects that you're trying to detect. And like I said earlier, how the size of the anchor boxes are decided is by looking at the ground truth annotations for your data set. So if you have smaller objects to be detected, your anchor boxes should reflect that. But yeah, you have the freedom to change it, definitely. You can start with the default one, and if that doesn't work, you can look into changing it. They do give you some options in later versions, I think, but it definitely can be played around with. Cool.
All right, great questions. Any more questions? One round, one last call for questions. All right. Yeah, no, thanks, Natasha, for the talk. We'll now move on to the next one. So Lu is going to talk to us about data fusion from text and images. So she's there, and if you can share your screen.
Sure.
All right, we see a desktop.
So
You can see one slide. I don't think that's the start though. There we go.
Okay.
Yeah, go ahead. Thanks, Lu.
Thanks for your introduction. And hello everyone. Now I would give a talk about cross-graph fusion method, and the method is proposed in an ICME paper in 2021. Firstly, I will start with an introduction to the focused research problem of the paper. Then I will show the related work, and then the detailed information of the proposed method will be given in the third section. And then I will talk about the dataset statistics and the experimental results. And lastly, we will have a summary of the paper. Okay, so the focused problem is about the multimodal marketing advertorial detection in social news. And the background is that the spreading and collecting information through the internet has become the norm. And nowadays, more and more people choose to post for profit advertorial in social news. And their aim is to leverage the news to promote the product. And I believe many of us may find similar content on social media every day. And however, because due to the absence of the network surveillance, there are a lot of malicious marketing information on the website, such as the misleading advertisements and unproven folk science. And this malicious marketing content may be capable of harming the social order and people's economic interest and even their health. And even the normal promotional advertisement can distract people's attention, and that's waste their time. So facing this phenomenon, automatically marketing intention detection is of great importance. And but how to develop an approach to automatically detect the marketing editorial is still a very challenging task. And firstly, the important marketing information is usually embedded in the multimodal content. Like sometimes the marketing content is embedded in the text. Like here in figure 1, we give an example of the editorials. And like in figure A, the words in red colors are editorial related information. So the information is only embedded in the text. But sometimes the marketing content is embedded in the image. Like here we can see in the figure B, there's only one image. Like the left image is showing a kind of food for a dog. So the marketing information is only embedded in the image, but sometimes both the images and the text are used to deliver the commercial information. This helps to grab the reader's attention. It's better than just a block of text or several images, but this brings a challenge for the analysis of commercial intent at the same time. The gaps between this multimodal data makes it difficult to fuse the imagery and the text for content marketing detection. And secondly, the real commercial content is usually concealed in the news content, such as local affairs and even the celebrity gossip. So an editorial contains not only the promotional information, but also the news value. So motivated by these challenges, the paper proposed a cross-graph fusion method in order to integrate the multimodal news content and thus extract the crucial information from the editorial detection. So here are some related work in the intent detection, because editorial is actually a piece of social news. So with the marketing intent. So the editorial detection is a kind of human intent detection. Human intent detection has been studied in a variety of applications. Like for example, the visual information is used to detect the human intent in human-object interaction, and the relationship between the photographer's intent and the viewer's attention is explored in order to improve the image analysis and the understanding. And the user's action is used as a supervision to detect the email intent in some paper. And the text-based user intent prediction is leveraged to support the customer service booths, and also the identification of the corresponding products of the hot trend on the social media is proposed. So these are the related work in intent detection. And so now let's move on the proposed method in the paper. And the cross-graph fusion strategy aims to learn soft assignment from the image graph and the text graph to a multimodal graph. And by this way, the important information from both image and the text is confused, and is fused and extracted from the extracted for the further prediction. And figure 2 shows the framework of the method. And here, the social news with multimodal component is the input of the network. And based on the input social news, the authors built 2 graph structures, GT and GI. And these 2 graph structures are constructed to represent the text and the image of the piece of social news. And in GT, we have sentence nodes, and the edges are constructed by the similarity between each pair of sentences. Like we calculate the similarity between each pair of the sentences, and there should be a threshold. And if the similarity is above that threshold, there will be an edge. But if the similarity is below the threshold, there won't be. And similar in the image graph, GI, we have image nodes, and the edges are constructed by the similarity between each pair of images. Here, A represents the node feature matrix, and H represents the adjacency matrix. And here we can find that the number of the nodes vary a lot, because writers usually add flexible numbers of images or sentences in a piece of news. And after the embedding of the first GCN layers, the text graph and the image graph are fed into the proposed cross-graph fusion model. And the output of the cross-graph fusion model is a fused graph structure representing the multimodal graph. And this graph is fed into a GCN layer and followed by a classifier for the decision making. And the authors use the cross-entropy loss. Now let's find out how the proposed cross-graph fusion works. Firstly, I want to give a short description about graph convolution networks. The general idea of the graph convolution network is to apply the convolution over a graph. Instead of having a 2D array as input, GCN takes a graph as an input. And the formula is shown here. And this formula describes the update of a single node embedding. And the node features are transformed by multiplying with a shared weight matrix W. For each individual node, we want to sum its neighbors up. So, and here, I is the current node, and J are all the neighbors node, and Cij is a constant, and sigma is an activation function. So from this we can find that GCN is the inherently closed, because they only propagate information within one graph, but they block the cross-graph information. So the aim of the cross-graph fusion is to fuse the text graph GT and the image graph GI into one multimodal graph G prime. As we know, a graph can be well described by a set of nodes and edges. So now the problem is converted to how could we get the feature matrix and the adjacency matrix of the fused multimodal graph. So in order to find the graph G prime. CGF, so-called cross graph fusion, learns an assignment that projects nodes from two separated graphs into one graph. The assignment is achieved by a learned assignment matrix P. So here we can find, in order to get the F prime and the A prime, we need to know P. And the P is so-called the assignment matrix. The node feature matrix F prime and the adjacency matrix A prime can be computed by the learned assignment matrix. Here, the author used but how could we get P? So here, the author used the second GCN and the fourth GCN layer to learn the matrix PT and the matrix PI, as like we can find the formula here. And here, J represents the softmax function applied row-wise in order to ensure the total assignment of each original node to be 1. And then these two learned matrix PT and PI are concatenated row-wise as the assignment matrix P. So now we can get the assignment matrix P. But how could we get the rest? Like, in order to learn the feature matrix F prime, besides P, we still need to know E. But what's E? The E matrix is a learned embedded matrix, so it's also be learned. So the first and the first GCN and the third GCN is used to learn ET and EM matrices, and these two matrices are concatenate. By concatenating these two matrices row-wise, we can get the embedded matrix E. So once we get matrix E and the matrix P, we can calculate the feature matrix F prime. But how could we get the adjacency matrix A prime? The adjacency A prime is computed by matrix P and the matrix A. Here we already got the matrix P, but how could we get the matrix A? The matrix A is the concatenation of the matrix AT and AI along the diagonal. Here we can find in the picture. And for the rest element, we fill that with all 0. And under this fusion strategy, a soft assignment is learned to integrate the images and the text of the social news. And the GCN is used to mining the intra-correlation within the modality in the method. And the cross-graph fusion strategy is used for mining the inter-correlations between multiple modality. And here are the experiment, the data sets used in the experiment. The experiments are conducted on 3 data sets, and there is no imbalance data problem. And the table 1 and the table 2 shows the statistics of the 3 data sets. And here is the experimental results in the paper. And the last row is the proposed method. And the method is an end-to-end method, and the model uses the ADAM optimizer, and also compare their methods with other baselines. And they compared with single modality methods such as SIFT and IGN and TGN and TF-IDF. And the rest of the methods are multimodal methods. from the results, we can find that their method already achieved the best performance. And overall, we can find the multimodal method performs better than single modality method, except the PF-IDF method. And because the second data set has the topic information of the advertorial, so in the second table, we can they give the detailed results of each topic class, and the third data set have the promotional extent information. So the third table gives the detailed results of each extent, and table 4 shows the evaluation study result on the 3 data sets. So now let's have a summary of this paper. And the research topic of this paper is to detect the marketing advertorial of multimodal content in the social news. And the paper proposed a cross-graph fusion strategy in order to integrate the multimodal content and discover the intercorrelations between the multiple modalities. And through the experiment results, they also verify the capability of their proposed method. And here are the references used in the slides. And thank you. I would be happy to answer any question.
All right, Lu, thank you very much for that. That was great.
Thanks.
Yes, any questions for Lu?
Hey Lu, that looks really cool. Just a few questions I had on that. If you can go back to that architecture diagram where you combine the text with the images.
Like this one?
Yeah. So you have 2 GCNs, right? One for combining the, one for building the using the text, the other one for the graphs.
Yes, yes.
I have 2 questions. First is, are there any different ways you can use to create the text graphs and the image graphs? And the second question is there any special differences you noticed in the requirements and the depths of like those 2 GCNs there, the ones in blue?
Yep. Sorry. I beg your pardon. What's your first question? You mean?
Okay.
And anyway.
Yeah. Okay. Sorry.
I didn't get you.
So maybe the second question, I'll bring that first. You have 2 GCNs in blue, one for sentences, one for images, right?
Yes. Yes.
Are there could you explain like any the design differences in them, like the number of layers, convolutions, attention?
These 2 GCN layer are different layers, though the weights are not shared between them. Yeah. And
right,
also
so both of them.
And also for the rest of the GCN, they are all not shared weight. So they,
okay.
Yeah. The GCN layer for the text graph is only used to embed the text graph, and the GCN layer in the image branch is to embed the image graph. Yeah.
Right. And both the GCN layers have there's 2 layers in the text version and the image version of GCN.
Yes.
Right. Thank you.
Yep.
And also, did you explore any different ways to create the image graph, or are there different alternatives if you need to create an image graph?
Yeah. Like you mean how to construct the image graph and the text graph? Yep.
Yes, please.
Yep. Like in a piece of news, there should be several numbers. There should be several images, and each image is treated as one image node. Like here we have 5 nodes, which means in this piece of social news, we have totally 5 images, and the ages between the nodes is decided by the similarity between the image pairs. Like if these 2 image pairs, the similarity between them is bigger than the threshold, so there should be an age. And if there's if the similarity between this image pair is lower than the threshold, there won't be an age. So that's how the image graph is built. And
right, and
yep.
you use cosine similarity there, or
Yes,
something different?
Cosine similarity. And for the text graph, the same, like because in text, the author may put several sentences in a block of text. So like there are 6 nodes, which means we have 6 sentences in this text block, and the ages are built based on their similarity.
All right. Okay.
Yep.
Thank you very much.
There are also one threshold in the text graph. So these thresholds are hyperparameter in the network, which is needed to be tuned.
Right. Got it. Got it. Thank you.
Thanks.
Yeah, cool. My question is sort of similar, because this would be cool, in my opinion, to apply it to medical imaging, for example.
Mm-hmm.
And the image graph you mentioned is between images, but do you know of ways where image graphs have been generated for a single image, maybe between patches or?
Yes,
something?
I think the direct way is to divide the medical image into patches and try to model their correlations between the patches, and then build the image graph. I think that's one of the one of the direct way to do that.
Yeah, exactly. Guy has a comment in chat. Exactly. So that would be really cool. I think that's a direct way to basically, fuse all of that data together as a graph. I mean, ultimately, I guess you could also do it within patients of an entire study as well. And so the graphs serve as like a meta-analysis of the patients of a study that have a particular, I don't know, disease or something. But yeah, cool. That's a very useful approach. Cool. Last call for questions. All right. Yeah, I think that's the end of it. Thank you very much, Lu, again for your talk. Thanks everyone for attending and those who are watching the recording. So that's the end of this session, and we will see you tomorrow for a couple of sessions on deploying your models once you have them. And of course, we're going to have a dive into quantum deep learning. So that should be exciting. All right. Thank you, everyone. See ya.
Thank you.